Hi everyone. In this video, we'll continue our discussion of mixtures of secant and tan, focusing on situations where there's an odd power of secant by itself. I mentioned in the previous video that's really the worst case scenario, so let's talk about why. So here's the big question in this video. How do we find the integral of secant to the n when n is an odd number? Notice we already know the integral of secant cubed. That should be on your formula sheet. So we've at least figured this out when n equals 3. And in order to figure that out, we had to use the parts formula and cause our integral to cycle. I'm proposing that the exact same strategy is needed for every odd power of secant. To convince you of that, let's see if we can apply that strategy directly to the integral of secant to the n. And in doing so, we're going to come up with a formula for what this integral is equal to in general. In order to integrate by parts, I need two factors to work with. So I'm going to split up my secants to form a factor of secant squared, which would remove two copies of secant. So what would remain would be secant to the n minus 2. So you can check that what I've just done, I've just split up my secants. This is still equal to the integral that we started with. Now, the reason I want to form secant squared is because it makes a really nice choice of g prime. And that's because secant squared has a really easy antiderivative. It's just tan x. So that's what we'll use as g. That means for f, we need to use this other factor. So let's differentiate this to form f prime. As a first step, since secant is being raised to a power, we need to apply the power rule. So the n minus 2 gets brought down in front, and then the power gets reduced by 1, resulting in n minus 3. Now, since it was secant which was raised to a power, we still need to apply the chain rule here, meaning multiply by the derivative of secant, which is secant x tan x. Also, we may as well simplify this formula for f prime while we're at it, and with all this, we're ready to apply our parts formula. The integral we want is equal to f times g minus the integral of f prime g. I've pulled out the n minus 2 since it's a constant anyway, and I simplified tan times tan as tan squared. So you can pause and confirm those details as necessary. Remember that we're trying to cause the integral to cycle here. Now, and the integral we've ended up with is secant to the n minus 2 tan squared, but the integral we started with is secant to the n minus 2 sec squared. So for cycling to happen, tan squared needs to be changed into sec squared. No problem, because we have an identity that can do that for us. And although it's tedious, let's not lose track of all this other stuff before we go on to the next step. Next, I'm going to expand, and when I multiply secant to the n minus 2 times secant squared, the result would be secant to the n, giving us the integral that we started with, which is a good thing. That's where our cycling is going to come from. I also need to expand onto this second term, and keep in mind that term is also getting multiplied by n minus 2. So when I form the integral of the second term, it's also going to have that n minus 2 in front, and it's going to be positive as a result of a negative being multiplied by another negative. Since secant to the n minus 2 times 1 is just secant to the n minus 2, this is the integral of our second term. You can pause and confirm it if necessary. Once again, let's make sure not to forget all this other stuff. Now that we've seen the integral of secant to the n on both sides, we've successfully caused our integral to cycle. So as usual, we want to collect both these terms together on the left-hand side. So on the left side, we'll now have n minus 2 copies of that integral after bringing that term over, plus the integral that was already there. On the right side, I haven't done anything yet with these other terms, but let's make sure to keep track of them for the next step. So far we've come up with this nasty result, but we're pretty close to the finish line. On the left side, I see n minus 2 copies of my integral, plus one more copy. So that gives me n minus 1 copies of the integral in total, right? N minus 2 plus 1 more is n minus 1. The right-hand side still just is what it is. Now, my objective here is to figure out what this integral is equal to, but that can now be determined if we multiply both sides by 1 over n minus 1. So we multiply this to the first term on the right side, and then also to the second term. With that, we can breathe a sigh of relief and state this as our formula for the integral of secant to the n. You should pause now and write this one down on your formula sheet. At first glance, this may not look like a very useful formula, since it really just shows that our integral is equal to another integral. And this other integral is still a power of secant, so it has the same form as the one we started with. But the advantage is that this new integral has a smaller power. And actually, the fact that it has the same form that we started with is a good thing, because it means this formula could be applied again to make the power even smaller if we wanted to. I'll show an example in just a moment. But for future reference, this is called a reduction formula. A reduction formula, more generally, is any formula which reduces an integral into something which is of the same form but simpler, such as having a smaller power. That's one example of what it might mean to be simpler. Since the reduction formula gives us a smaller power, the idea is that we can use it over and over again to get smaller and smaller powers until eventually we get something that we can manage. Let me show you what I mean by that with an example. So let's calculate the integral of secant to the 5 using the reduction formula at the top of the screen. Literally, all we need to do is recognize that n equals 5 in this case. So in my reduction formula, anywhere you see an n, put a 5 instead. And after simplifying, you'll get this result, which you can pause and confirm for yourself. What this equality really tells me is that if I want the integral of secant to the 5, then I need the integral of secant cubed. Now, we already know the integral of secant cubed, but if we didn't know it, then the reduction formula could tell us what it is. So let's try it just for practice. To figure out what the integral of secant cubed is equal to, we can apply the reduction formula here where n equals 3. And make sure to use brackets to indicate that the 3/4 in front is still being applied to the entire result. When you plug n equals 3 into the reduction formula, after simplifying, you'll come up with the results that I just put in these brackets, which you can pause and check for yourself. So after doing that, we've come closer to figuring out the integral of secant to the 5. All that remains now is to evaluate this remaining integral of secant x. And we definitely know the answer to that integral already. It should be on your formula sheet, so you can just copy it down there. So after putting this all together, we've got our integral of secant to the 5, which is what we wanted. Just don't forget the plus c. You can see how messy things get when you're working with odd powers of secant, which is why I called this the worst case scenario. But if you look back on what we just did, the idea behind what we're doing is simple. Every time we apply the reduction formula, the power gets reduced by 2. So in this example, the power of 5 got reduced to a power of 3, and then when I applied the reduction formula again, the power of 3 got reduced to a power of 1. For really large values of n, it would be necessary to apply this formula quite a few times before we get something manageable, but at least we can be assured that each time we reduce the power, we are getting closer to an answer that can be found eventually. I've made a big point about referring to odd powers of secant, but what about even powers? Well, in the proof of the reduction formula, there's nothing saying that n can't be even, so that does work just fine. But the reduction formula is never necessary with an even power, so my preference is to avoid it, since personally I find that formula not only tedious, but also difficult to remember. To do this without the reduction formula, just make use of the strategies we talked about in the previous video. If we form secant squared to use as du, the remaining powers would all be even, so a simple substitution should do the job just fine here. In this case, u would need to be tan x in order for du to be secant squared x, and then an identity could be applied to change my secants into tans. After that, tan could be called U, making for a successful substitution. And then it's just a straightforward antiderivative that you can check for yourself. I encourage you to pause here and try solving this problem using the reduction formula instead. Because although it's not my preferred method for this problem, it doesn't hurt to just practice using that formula. By the way, if you do use the reduction formula, your answer will not look the same as the one that I just put here. And that's just because with trig identities, there's all sorts of ways to make the same answer look completely different. This is all I have for now, so I'll wrap things up there and see you next time.